Welcome to my presentation titled Photo-induced Force Microscopy, short PiFM, a new technique at the biomineralogist's fingertips. My name is Laura Otter. I obtained my bachelor's and master's degree from the University of Mainz in Germany, the latter in cooperation with the Max Planck Institute for Chemistry, before I went on to earn my PhD at Macquarie Uni in Sydney, and am now a postdoctoral fellow with the Research School of Earth Sciences at the Australian National University in Canberra, Australia. PiFM is a quite spectacular new technique that, in my opinion, has great potential to become one of those tools of the trade. Put simply, it merges the advantages of atomic force microscopy, which is a sensitive high-resolution surface probe, with absorption spectroscopy similar to FTIR. I am going to present its working mechanism and demonstrate its application to the biomineral nacre. I hope you'll enjoy. Let me start with an overview of PiFM's historical development. So first off, it's critical to note that there wouldn't be a PiFM today if not for the development of the atomic force microscope, short AFM, invented in 1985 by IBM. An AFM is an incredibly sensitive scanning probe that delivers information like sample topography maps and mechanical property maps at resolutions of few nanometers. However, these phase identification comparable to FTIR or Raman was not routinely available, and so an AFM-based phase ID technique was several times developed, all with their different pros and cons, and PiFM just happens to be the most recent and most advanced one of them all. As PiFM was only developed in 2010, it is still in its early developmental stages, and a lot of method development and technical improvement is still ongoing. But as you can also see here, applications took really off in 2014, and today PiFM has been applied to many areas in physics, chemistry and biology. As its range of applications is ever growing, we propose that it will likely become equally beneficial to a wide range of geochemical and environmental research applications. And convincing you of this is the rationale of this talk. But what is this PiFM now exactly? Let's have a look at the instrument. PiFM is performed with a slightly modified AFM instrument, referred to as the vistascope, that you can see here. This instrument features an additional laser that is tunable not only across a wide range of pulse repetition rates, but also with regards to wave number range. Secondly, a parabolic mirror is used to shine the laser onto the sample. Thirdly, a specialized software package handles the evaluation of the spectral and hyperspectral maps, lines and spots together with the topography data. But how does PiFM now work exactly? As the basis of PiFM is the atomic force microscope, we need to talk about how this works first. Put simply, AFM is an incredibly sensitive oscillating cantilever that performs a tapping movement just above the sample surface. Without touching it, this is also called the dynamic AFM mode. While the cantilever taps, the sample stage moves in X, Y, and Z to record the sample's topography in a pre-selected map area. While the cantilever taps and the stage drives, all positions are recorded by the AFM feedback laser and its corresponding photodetector. Now the parabolic mirror reflects the PiFM laser light onto the area that is tapped by the cantilever, and the PiFM laser sweeps across a range of wave numbers. At certain wave number regions, the sample's molecules absorb the laser light more strongly and produce a dipole at the sample surface. And a mirror dipole is induced at the cantilever's tip. The laser light, or photo-induced dipole-dipole attraction force between sample surface and tip, is highlighted here by these red arrows. Lastly, the PiFM laser is also set to match its pulse repetition rate to the oscillating movement of the cantilever, and this amplifies the photo-induced force signal at each stage position. To be precise, this type of map is called a hyperspectral map, as each pixel of the map contains the whole spectral range of the PiFM laser. But of course, the same region can also be analyzed without sweeping the laser across a range of wave numbers to produce a fixed wavelength map. And spot and line measurements are of course also possible. Let's talk about the differences between PiFM and FTIR. While FTIR uses a polychromatic ER source containing all wave numbers, and thus records the sample's ER absorption for all wave numbers simultaneously. But the polychromatic light source and the optical detection mechanism also mean that the resolution is limited to half of the source's wavelength by a phenomenon called the diffraction limit. Hence, it cannot provide nanoscale resolution. PiFM, on the other side, uses the monochromatic light source of a laser and must therefore record absorption features sequentially for all wave numbers. As the signal is not an optical one, but derives, so to speak, indirectly from the dipole-dipole attraction force, there is no limitation by the diffraction limit, and thus analysis with a spatial resolution down to a few nanometers is possible. Despite their differences in terms of spatial resolution, both techniques produce virtually identical peaks, as you can see below here. And this is great because we can use FTIR databases for an easy interpretation of our PiFM data. But let's talk applications now. I want to make the case here that PiFM is extremely well suited for the characterization of biominerals that are usually quite challenging to analyze. Let me list here some of the challenges associated with the analysis of biominerals, and then I will explain how, I believe, PiFM can offer some solutions. So firstly, biominerals are very beam sensitive, and electron beams and lasers can easily induce phase transformation. However, the PiFM lasers use low energies of 1 or less than 1 milliwatt, which is much less than traditional micro-Raman or FTIR uses, and are ideally suited to analyze samples without inducing phase transformation. Secondly, biominerals are usually hydrated, and dehydration under a beam or in a vacuum chamber can easily change the structure, phase, and morphologies, a problem often encountered in electron microscopy-based techniques. But with PiFM, no vacuum is required, as all measurements can be performed at ambient pressure and temperature. Lastly, biominerals are usually nanocomposites, meaning they consist of an organic and an inorganic phase intimately joined in a 3D architecture across several length scales. And so far, traditional phase ID techniques like Raman, FTIR, EBSD, or even TKD can struggle to resolve the smaller portion of these length scales, and most importantly, do not offer in situ ID of organic phases. This is where PiFM really excels. It can map organic and inorganic phases equally well and produces topography maps along with the phase maps, which really helps to understand a sample. The PiFM maps have a spatial resolution of down to 5 nanometers and a low depth penetration down to 2 nanometers. So this gives a high resolution insight into structure and phase composition of the sample. This altogether makes PiFM a very intriguing technique for the characterization of biominerals. An example for such a complex biomineral system is nacre, also called mother of pearl. It can be found lining the inside of mollusk shells, like in the case of the Acquoia pearl oyster here, or forms lustrous outside of cultured pearls, like in this Acquoia pearl here. Nacre forms via stepwise crystallization of transient precursor phases in an exothermic downhill reaction. The phases include amorphous calcium carbonate, ACC, Vaterite, and the final fully crystalline product, aragonite. Nacre's mesoscale architecture consists of polygonal mineral tablets that are enveloped by organic membranes. At the nanoscale, each tablet is speckled with vast numbers of tiny organic inclusions. We know today that these inclusions are critical for the material's mechanical resilience, meaning its excellent toughness and fracture resistance. You can perhaps get a good idea of this here when looking at the super high magnified cross-section of nacre. This is imaged in the transition electron microscope before, under, and after mechanical loading. During compression, both tablets interlock across the organic membrane, and the organic inclusions here in the little insets rotate and deform. See how everything jumps back to its original state when the load is removed. This elasticity and structural resilience is only due to the organic content of nacre, even though it's just about 3% total organic content, and we don't see any elasticity and resilience in pure geological aragonite. Given the importance of organics and the phase ID was so far not available in situ, we were keen to have a closer look with PiFM. Here you see the AFM topography map of Acquoia pearl oyster nacre. Highly magnified, so you just see a part of 2 nacre tablets on either side of the organic membrane, and the little superficial pits are organic inclusions. It is about the same magnification as the TEM image before. The PiFM composite map here shows the distribution of aragonite by mapping the aragonite main peak at 1471 wave numbers. It appears here in both tablets, and it's not observed in the membrane. The membrane and inclusions are mostly red and green, which are fingerprint regions for amides, the amide 1 and amide A region to be precise. And put simply, amides can be understood as one of the main ingredients of proteins. Lastly, we can put both datasets together to form a 4D dataset that includes topography with phase information. Note the red little dots marked by the white arrowheads. Those are subsurface inclusions, as they don't show a pit in the corresponding topography image. These inclusions are very close to the surface. Our depth penetration here is about 5 nanometer, but they were not opened during polishing. Proteins explain the elastic behavior observed in the mechanical experiments here by Jim et al. Very well, and they also agree with the atom probe data by Ida et al., in which high amounts of carbon, nitrogen, and hydrogen were reported from inclusions and membranes in nacre. This brings me to the outlook part of this talk, and I'm excited to say that we have just received our very own VISTA scope in Australia, at the Australian National University. And you can see here it all is still boxed up. And we aim to apply it broadly to many different areas of geochemistry. Personally, I will use it to investigate nacre and other biomineral systems, including their transient metastable phases. So this concludes my presentation. I hope I could convince you that PiFM is a promising new technique for biomineralization and geochemistry in general. And I thank you for your attention. Thanks also to my co-workers here at ANU, Macquarie, and Molecular Vista. If you would like to learn more, see our open access cutting edge article published in JJR and see the next slide for references. Thanks for listening.